Hey everyone! In this lesson we're gonna go over a few bitwise operations and numbers, stuff that'll come in handy when we start learning about bitwise operators. So what fundamental data types do you remember? We've got short, unsigned, int, long, unsigned, long, and unsigned, long. Among the character types, we've got char w, char t, char at, char 16t, and char 32t. And of course, there's the logical type, bool, and don't forget about float, double, and long double. I've made a table showing how many bytes each of these types takes up in memory. You already know this from one of the first lessons, but now that we understand numbers are stored in binary, we can take a closer look at how exactly they're represented in memory. Let's start with something simple, the bool type. It takes up 1 byte, even though it can only hold 2 possible values. So the first question is, why does it need a whole 8 bits if 1 bit would be enough for 2 values? The thing is, at the hardware level, CPU and RAM, memory is addressed by bytes, not by individual bits. That means the processor can only read and write full bytes, 8 bits, at a time, not single bits. So if bool were just 1 bit, the CPU would have to read the entire byte, modify that single bit, and then write it back. That would make the architecture more complicated and slow down operations. That's why the smallest type in memory must take up at least 1 byte, no less. Now let's talk about the values it stores. The literal true equals 00000001, which is the number 1. That's why I've said before that true is always equal to 1. The literal false equals 000000000, which is the number 0, so false is always 0. But we can also assign any other number to a bool variable. For example, we know that the number 10 easily fits into 1 byte. It's stored as 00001010. However, if we assign any number other than 0 or 1 to a variable of type bool, it automatically turns into 1, or more precisely, the literal true. Now let's move on to character types. We know they store characters, but here's the scary truth. All of these types are technically numeric. Inside, they don't actually store characters, they store numbers. Let's start with the one you already know, char. It's made up of 8 bits. When you assign a character to it, like this, that character gets converted into its numeric representation in binary form. For example, the uppercase letter A equals 01000001. That's what's actually stored inside the variable, and if we treat that as a number, it's 65 in the decimal system. You can even hover your mouse over the character in most IDEs and see that number yourself. You can also assign integer literals to character variables. We know an integer literal is of type int, and it's stored in memory like this, so when you assign it to a char, it just gets converted accordingly. So why do we see characters instead of numbers when we print char variables to the screen? Because cout checks the variable's type before printing. When it sees a char, it knows it needs to show the symbol from the ASCII table, not the number. So if the value is 65, cout looks up the ASCII table and displays the character whose code is 65, the letter A. The char type is kind of special because it can actually hold negative values in some cases. The C++ standard doesn't specify whether char should be signed or unsigned. That's up to the compiler. For example, in Visual Studio, char is signed, meaning it can store negative numbers. If I assign -50 to it, what happens? Well, there are no negative symbols in the ASCII table, so you'll just see some random garbage on the screen. On my system, it shows a weird symbol like this one, but internally, the variable really does store -50. You can easily check this by casting the char to an int. Notice that most integer types take up at least 2 bytes. So what if you want to work with numbers that only needs 1 byte? That's exactly what char is useful for. You also know about the keywords unsigned and signed. You can use both with char. Unsigned char makes the type strictly unsigned. It can only store 0 and positive numbers. Signed char makes it strictly signed, meaning it can store negative numbers too. Now let's move on to the other character types. wchart works the same way as char, except it takes up 2 bytes, which means it can hold a wider range of values or symbols. As of char AT, char 16T, and char 32T, these are strictly unsigned types according to the C++ standard. Now let's move on to the larger integer types, the ones that also store whole numbers, but like char, cout always prints them as numbers, not as characters. The first thing you need to understand is how to figure out the range of values each type can hold. Let's go back to char for a moment, specifically unsigned char. In this type, all bits are used to represent a positive number. If all bits are 0, the value is 0. If all bits are 1, the value is 255. How do you know that? Easy, just use the calculator. Open it, switch to programmer mode, and type 8 ones in binary. You'll see that in decimal that's 255. So the minimum value an unsigned char can store is 0 and the maximum is 255. That gives us 256 possible combinations in total. But what happens if a type can also store negative numbers? How are negative numbers actually stored in memory? Well, let's figure that out using signed char as an example. If a type supports negative values, the computer needs a way to store the sign, whether the number is positive or negative. For that, the leftmost bit of the type is used. If that bit is 0, the number is positive. If it's 1, the number is negative. That means we now have only 7 bits left to represent the actual number instead of all 8. Because of that, the range of possible values gets cut in half. So how do we figure out the smallest negative number using a calculator? Well, a signed char takes up 1 byte. In the calculator's programmer mode, you can choose the bit size in the center. Byte equals 8 bits, word equals 16 bits, dword equals 32 bits, and qword equals 64 bits. Select byte. In the earlier lesson, where we looked at data types, we saw that signed char ranges from -128 to 127. So the smallest number, -128, looks like this in binary: 1, 0, 0, 0, 0, 0, 0, 0. The leftmost bit is 1, meaning the number is negative, and the rest are zeros. Together that gives us -128. Notice that if the leftmost bit weren't used as a signed bit, this same pattern would represent 128 instead. And what about the largest number for signed char? We set the leftmost bit to 0 and fill the rest with ones. 0, 1, 1, 1, 1, 1, 1, 1. That's 127 in decimal. Why am I explaining all this? Because the same logic applies to other types like short, int, long, and long, long, which can also store negative values. Now you know that for all of them, the leftmost bit is reserved for the sign, and the remaining bits store the actual value. So, whenever you dedicate 1 bit to the sign, the maximum positive value the type can store is cut in half. Everything I just explained about unsigned char and signed char applies to all integer types. The only difference is that they occupy more memory. For example, short ranges from -32,768 to 32,767, while unsigned short goes from 0 to 65,535. That's because the keyword unsigned tells the compiler to use all bits for the value itself, no sign bit, which means you lose the ability to store negative numbers, but your positive range doubles. Now let's move on to the last and most complex topic, floating point types. Things get more interesting here because these numbers aren't stored like regular integers. Instead, they follow the IEEE 754 standard, which splits a number into three parts: the sign, the exponent, and the mantissa, also called the significand. There's a formula that defines how floating point numbers are stored in memory. Yeah, it looks scary, but don't worry, you don't have to memorize it. On the left, you'll see the word sign. That determines whether the number is positive or negative. If it's 0, the number is positive. If it's 1, it's negative. So right away, 1 bit is used just to store the sign. Next is the mantissa, which represents the fractional part of the number. It's basically what gives the number its precision. For a float, 23 bits are reserved for it. For a double, 52 bits. And for long double, at least on my system and compiler, it's also 52 bits. Then we have the exponent, which defines the scale of the number, how large or small it is. The exponent uses 8 bits in a float and 11 bits in both double and long double. Finally, there's something called the bias, an offset added to the exponent. It's used so that the exponent can represent both positive and negative powers of 2. The idea is simple. When storing the number, we add the bias. When reading it, we subtract it. The bias value is 127 for float and 1023 for double and long double. So here's how it all fits together. Float, 4 bytes, or 32 bits. 1 bit for sign, 8 bits for exponent, 23 bits for mantissa. Double and long double, 8 bytes, or 64 bits, 1 bit for sign, 11 bits for exponent, and 52 bits for mantissa. Let's look at an example. Say we have a float variable with the value 5.75f. We know a float takes up 4 bytes. Let's try to convert it into binary form. The number has an integer part and a fractional part, so we convert them separately and then combine them. The integer part, 5, in binary is 101. The fractional part, 0.75, is a bit trickier. You get it by multiplying by 2 repeatedly until you reach 1. So 0.75 times 2 equals 1.5. We write down 1 and subtract 1. It equals 0.5. So 0.5 times 2 equals 1.0. We write down 1. So after 2 steps, we're done, meaning the fractional part becomes 0.11 in binary. Now we combine them. 101.11. Next, we normalize it into scientific binary form. That's 1.x times 2 of power n. And we move the binary point left until only one remains before it. So it's 1.0111 times 2 of power 2. Here, n equals 2 since we shifted 2 places. Now we add the bias. For float, the bias is 127, so 127 plus 2 equals 129. In binary, 129 equals 1,000,000,1. The mantissa is what comes after the 1, that's 0111. We only have 4 bits so far, but the mantissa field must be 23 bits. So we pad the rest with zeros to the right, giving us 23 bits total. Finally, the sign bit, our number is positive, so it's 0. Now we put everything together, sign, exponent, mantissa in that order. If you split it into bytes for clarity, that's the full 4-byte binary representation of 5.75 in memory. And that's how floating point numbers are stored. Do you need to memorize the formula? No. But it's good to understand the logic behind how these numbers actually live inside your computer. We figure out how numbers are stored in memory. I'd also like to talk about how numbers are added and subtracted. Only integers, so your head doesn't hurt. We'll look at the unsigned char type for simplicity, because it only takes up 1 byte and we know it's numeric. Let's create 2 variables of this type and assign them some simple numbers. Then we'll store their sum in the 3rd variable. How does the computer actually add these 2 numbers if they're stored in binary form? We know that the value stored in sum will be 56 in decimal, but how do we determine why exactly it's 56? Let's figure it out. First of all, computers use bit-by-bit addition. Bits are added according to the following rules. If we add 0 to 0, the result is 0. If we add 0 to 1, or vice versa, 1 to 0, the result is 1. If we add 1 to 1, the result is 1, 0. Let's look at our example. I wrote down the binary forms of the numbers 20 and 36. We start adding them bit by bit, beginning from the right. 0 plus 0 equals 0. 0 plus 0 equals 0. 1 plus 1 equals 1, 0, but we can only write 1 digit. So we write 0 in this position and the 1 moves to the next column on the left. We keep it in memory. Next, 0 plus 0 equals 0, but we still have that 1 in memory. So we add 1 to 0 and get 1. Then 1 plus 0 equals 1. 0 plus 1 equals 1, 0 plus 0 equals 0, and 0 plus 0 equals 0. The final number looks like this, and that's 56. That's exactly how numbers are added inside the computer. But we can also write mathematical expressions using different types. We know that their types get converted to higher ones according to the type hierarchy. I talked about this in a previous lesson. For example, here we have types char, int, and short. We know that during any operation, char is always promoted to int. The int type is 3 bytes larger. In binary form, the new bytes just get filled with zeros. Then the 2 numbers are added together and the result, which takes up 4 bytes, gets compressed into 2 bytes. How? Simply, the left 2 bytes are cut off. The remaining 2 bytes fit into the short type. The same process applies to all other integer data types when performing mathematical operations on them. Let's talk about negative numbers. As an example, we'll take the sign char type because it's the smallest one. We already know that the leftmost bit in it is reserved for the sign. It equals 0 if the number is positive and 1 if it's negative. But what does it look like in binary form? First, take the number 50 and convert it into binary. I've put the bit responsible for the sign in parentheses, then we invert every bit of that number, meaning we turn every 0 into 1 and every 1 into 0. We get this number. I'll mark the inverted number with the tilde symbol. Why? You'll find out in the next lesson. So here's what we get. Next, we need to add 1 to that number. We add from right to left. 1 plus 1 is 10. We keep the 1 in memory. 0 plus 0 is 0. We add the 1 from the memory, so we get 1. 1 plus 0 equals 1. 1 plus 0 equals 1, 0 plus 0 equals 0, 0 plus 0 equals 0, 1 plus 0 equals 1, and 1 plus 0 equals 1. The final number is minus 50. This is how it looks in memory. When you write minus 50 in your code, the minus sign is actually an operation performed on the positive number 50. Specifically, it does 2 things. It inverts all the bits of that number and then adds 1. And that's easy to prove. Let's try adding 50 plus minus 50. The result should be 0, right? Here are their binary forms. Using the same bitwise addition rules, let's calculate. 0 plus 0 equals 0. 1 plus 1 equals 1, 0. 0 plus 1 equals 1. We add the 1 from the memory, that gives 10. 0 plus 1 equals 1, add the 1 from the memory, gives 10. 1 plus 0 equals 1, add the 1 from the memory, gives 10. 1 plus 0 equals 1, add the 1 from the memory, gives 10. 0 plus 1 equals 1, add the 1 from the memory, gives 10. And 0 plus 1 equals 1, add the 1 from the memory, gives 10. And here we notice that we run out of bits, but there's still a 1 left in memory. That's the 9th bit, and it doesn't fit into the sign chart type, so it's simply discarded. What's left are all zeros, or just the number 0, and there's our proof. Now, how are numbers subtracted in a computer? It's actually pretty clever. They're not really subtracted, they're added. One of the numbers just gets turned into a negative and then they're added together. Here, we're trying to subtract 20 from 30, so 20 gets converted into minus 20. How to do that, we've just learned. Then they're added together, and how to do that we also just learned. And that's exactly how all numbers are subtracted in a computer. I won't go into multiplication, division, or modulus division. If you want, you can learn that on your own. All of this is optional information. I've never actually needed it at work, but thanks to it, I understand much better how bits work, and that's something we'll need in the next lesson. And the last thing in this lesson is runtime errors called overflow and underflow. Let's take a look at the last block of code. Once again, for simplicity, we'll use the unsigned char type. We know that the maximum value it can store is 255, but if we add 200 and 200, we get 400. 400 won't fit into the variable sum. So what happens then? Let's convert these numbers to binary. We get this number for both of them. If we add them together using binary addition, we get 400, which looks like this in binary form. Here we have 9 bits, but the unsigned char type can only hold 8 bits. What happens next? The 9th bit simply gets discarded. As a result, we're left with these 8 bits. Their value is 144. And that's exactly what gets stored in the variable. So when you try to go beyond the limits of a type's value range, you get problems like this. If you go past the upper limit, in other words, the maximum value, the error is called overflow. If you go past the lower limit, in other words, the minimum value, it's called underflow. So be careful when working with small data types. Don't forget that they're not limitless. They all have their own value ranges. And that's it for this lesson. Thank you all for watching. If you enjoyed the video, you can support me in the following ways. Give this video a like, leave a comment below, subscribe to the channel if you haven't already, or send a donation, either through the link in the description or by using the thanks feature on YouTube. Also, don't forget, any theory is meaningless if you don't reinforce it with practice. I have separate practical lessons available only to channel sponsors. In those, I give lots of exercises based on all the lessons on the channel, and I also show how to solve them. So if you want to really grow as a programmer, consider becoming channel sponsor to get access to the practical lessons. See you in the next lesson, and bye everyone!